Hello everybody. In this video we are going to be looking at the solutions to the Honors Waves and Vibrations homework problems 6 through 10. Well, let's get started with problem number 6. A fisherman notices that wave crests pass the bow of his anchored boat every 3 seconds. He measures the distance between the two crests to be 6.5 meters. How fast are the waves traveling? So I know the period of the wave is 3 seconds because that's how long it takes to go from one cycle from crest to wave crest. So my period is 3.0 seconds. My wavelength, the distance between two crests, is 6.5 meters. And remember, for wavelength, we use the Greek letter lambda. And we are looking for the speed of the wave. In order to find the speed of the wave, I'm going to need to know the frequency of the wave, and I can find the frequency from the period. I know the period was 3 seconds, and the frequency is the inverse of the period, or 1 divided by the period. So 1 divided by 3 seconds is going to give me 0.33 hertz. Now I can find the speed of the wave because I have the frequency and the wavelength. And I know wave speed is frequency times wavelength. So 0.33 hertz times 6.5 meters will give me a wave speed of 2.2 meters per second. Problem number 7. A sound wave in air has a frequency of 262 hertz and travels with a speed of 343 meters per second. How far apart are the wave crests? And the wave crests in this case would be analogous to the compressions of the wave because a sound wave is a longitudinal wave. And if you don't know what that is, see the riveting video I did on the PowerPoint, and that will tell you what a longitudinal wave is. So in this problem, we are given the frequency of 262 hertz. We are given the speed of the wave at 343 meters per second, and we're being asked to find the wavelength. We're going to start with our wave speed formula, V equals F times lambda. In this case, we do want to solve for lambda, so solving for lambda will give me lambda equals V divided by F. I plug in my known values for the velocity and the frequency, and that will give me a wavelength of 1.31 meters. Problem 8. AM radio signals have frequencies between 550 kilohertz and 1600 kilohertz and travel with a speed of 3.00 times 10 to the 8th meters per second. So we're given two frequencies that represent the range of AM radio signals. And those two frequencies are, the first one is 550 kilohertz, which I know I need to convert to hertz. So it'll be 550 times 10 to the 3rd hertz. And my second frequency, which represents the upper range of AM radio signals, is 1600 kilohertz. And that is going to equal 1600 times 10 to the 3rd hertz. By the way, does anybody ever listen to AM radio anymore? I don't even know if you guys know what AM radio is. I don't even know if you guys know what radio is at this stage. I have no idea. All right, what else do we have here? We have the speed of the wave, which is 3.00 times 10 to the 8th meters per second. By the way, get used to that value. We're going to be using an awful lot moving forward because that is our speed of an electromagnetic wave, which includes the speed of light. And I should say in a vacuum. Let me just preface that by saying that's in a vacuum. We get to know that value pretty well. That's going to be kind of like our gravitational constant of 9.80 meters per second squared. It's one of those things that we're going to be plugging into a lot of stuff. All right, the first part of this problem wants us to find the wavelengths for each of the frequencies we're given. So we want to find the wavelength of the 550 kilohertz frequency and the wavelength of the 1600 kilohertz frequency. And For both of these, we are going to use our wave speed formula, solving for wavelength. So we're going to have lambda is going to equal the velocity divided by the frequency. So for the wavelength of my 550 kilohertz frequency, I know it is going to be my value for the speed, which is 3.00 times 10 to the 8th meters per second, divided by 550 times 10 to the 3rd hertz, and that is going to give me a wavelength of 545 meters, or 550 meters rounded to two significant figures. My second wavelength for the 1600 kilohertz frequency is going to be my wave speed of 3.00 times 10 to the 8th meters per second, divided by that frequency 1600 times 10 to the 3rd hertz. Remember, we always have to convert to hertz. And do that math out, and I'm going to get a wavelength of 188 meters, which would round to 190 meters to two significant figures. Part B of problem 8 tells us that on FM, the frequencies range from 88.0 megahertz to 108 megahertz and travel at the same speed. What are their wavelengths? So we're going to do the same procedure here. I know that my wave speed is still 3.00 times 10 to the 8th meters per second. And now my range of frequencies for the FM band are 88 megahertz, which I convert to hertz. So that will be 88.0 times 10 to the 6th hertz. And the upper range of the FM band is 108 megahertz, which would be 108 times 10 to the 6th hertz. So to find the wavelength of my 88 megahertz frequency, I would divide my velocity by that frequency. So 3.00 times 10 to the 8th meters per second divided by 88.0 times 10 to the 6th hertz will give me a wavelength of 3.41 meters. To find the wavelength of my 108 megahertz frequency, I will divide again 3.00 times 10 to the 8th meters per second by my frequency of 108 let me try that again, 108 times 10 to the 6th hertz, and that will give me a wavelength of 2.78 meters for the 108 megahertz frequency. Problem 9. A water wave travels a distance of 15 meters in 1 minute. When this wave passes a point where a cork is floating in the water, it causes the cork to move up and down 12 times in 15 seconds. In this problem, we are given the distance of the wave travels, which is 15 meters. The time it takes to travel that 15 meters is 1 minute or 60 seconds. When the cork bobs up in the water, it's going to bob up and down 12 times. So the number of cycles that it undergoes is 12, and the time it takes to undergo those 12 cycles is 15 seconds. The first thing they want us to find is the wave, the speed of that wave. So to find the velocity, I know I simply have to divide the distance the wave travels by the time it takes to travel that distance. So it travels 15 meters in 60 seconds. 15 divided by 60 is going to give me 0.25 meters per second. I do have to round that to one significant figure, so that would then round to 0.3 meters per second. Part B of problem 9 asks, what is the wavelength of this water wave? So we need to find the wavelength. In order to find the wavelength, I know I'm going to need the frequency of the wave. And to find the frequency, I know I have to divide the number of cycles it undergoes by the number of seconds it takes to undergo those cycles. So frequency is cycles per second. So it undergoes 12 cycles in 15 seconds. So 12 divided by 15 is going to give me a frequency of 0.8 hertz. One quick note on that. Just remember, frequency is cycles per second. So whenever I have frequency, I know that my time factor is going to want to be in the denominator. It's going to want to be in the bottom half of the fraction, as we see here, because remember, hertz is equal to seconds to the -1, or 1 over seconds. So for frequency, my time value seconds always has to be in the denominator. For period, the time always has to be in the numerator. So period would be seconds per cycle, but frequency is cycles per second. To find the wavelength, I use my wave speed formula, solve that for lambda. So lambda is going to equal velocity divided by the frequency, and the velocity I found in the first part of the problem, and that was 0.25 meters per second, and my frequency is 0.80 hertz. And that is going to give me a frequency, or I'm sorry, a wavelength of 0.31 meters, and it really should probably just say 0.3 meters. It probably should be one significant figure. Part C of problem 9 asks, what is the period of this water wave? So we are looking to solve for the period. I know that my period is the reciprocal of the frequency. So I just simply need to take my frequency that I determined in part B and just take the reciprocal of that. So the period is 1 divided by the frequency. 1 divided by 0.80 hertz is going to give me 1.2 seconds. So my period for this, this wave is 1.2 seconds. Problem number 10 asks us to calculate the frequency in hertz of each of the following. And the first thing they want us to find the frequency of is a new moon, throwing a little astronomy at you guys here. And the period of the moon, it tells us, is 27.3 days. So again, we're looking for the frequency. Well, I know the period is 27.3 days, but I need to know what that is in seconds. So I have to convert from days to seconds. I know there's 24 hours in a day, and there are 3,600 seconds in an hour. By the way, before you started physics, did you know how many seconds were in an hour? Or is that something that you learned here? I just want to prove that you learned something in this class. When I do that math out, I'm going to have a period, or 27.3 days, is going to be equal to 2.36 times 10 to the 6th seconds. So in order to find the frequency, I simply need to take the reciprocal of the period. So 1 divided by 2.36 times 10 to the 6th seconds is going to give me a frequency of 4.24 times 10 to the -7th hertz. The second thing they want us to find the frequency of is the length of a day on Earth. So I know the period of 1 day, I need to convert that to seconds. So 1 day will equal 8.64 times 10 to the 4th seconds. Once again, to find the frequency of that period, I simply take the reciprocal of the period. So 1 divided by 8.64 times 10 to the 4th seconds will give me a frequency of 1.16 times 10 to the -5th hertz. Part C asks us to find the frequency of a breath, and we are assuming that the normal breathing rate is 8 to 12 breaths every 60 seconds. So once again, we have a range, so we're going to have to find the period and the frequency for each of those values. So for my first period, again, I need to find the number of seconds per cycle. Remember, period is seconds per cycle. So for the lower end of the range, 8 breaths in 60 seconds, I know that the time value is 60 seconds, and the number of cycles within that 60 seconds is 8. So 60 seconds divided by 8 is going to give me 7.50 seconds. For the upper range of my breath is going to be 12 breaths in 60 seconds. So again, my time period has remained the same at 60 seconds, but now I have 12 cycles within those 60 seconds. 60 seconds divided by 12 is going to give me a period for the upper range of 3.75 seconds. To find the frequency for my lower range of 8 breaths per second, I simply take the reciprocal of my period of 7.50 seconds, and 1 divided by 7.50 seconds will give me 0.133 hertz. To find the frequency of the upper range of 12 breaths in 60 seconds, I take 1 and divide it by the period, which was 3.75 seconds. And when I do that, I'm going to have a frequency of 0.267 hertz. So the range of frequencies I am going to have for breath is going to be 0.133 hertz to 0.267 hertz. And the last part of problem 10 asks us to find the frequency of a heartbeat, assuming a heart rate of 1.0 to 1.6 beats per second. So we're going to skip finding the periods here and just go right into finding the frequencies, because I know the frequency is the number of cycles per second. So in the where we calculated the period, we needed our time value in the numerator. To find the frequency, we need our time value in the denominator. So for the lower end of our range of heart rate, which would be 1 beat per second, I know that there is 1 cycle in 1 second. So 1 divided by 1 equals 1. And for the upper range of my heart rate, 1.6 beats per second, again, the number of cycles is 1.6, and the time value is still 1 second. So 1.6 divided by 1 second is going to give me 1.60 hertz. So the range of frequencies for a heartbeat is going to be 1 hertz to 1.60 hertz.